Good evening, everyone. I'm Rochish, and I'm going to talk on observation of subcritical instability in experiments and simulations in charge drops. And the work was done around 2 years ago by my PhD students Neha and Mohit, and they are now in Karlsruhe Institute of Technology. And the work was done in collaboration with Professor Maya, who now I don't see in the audience. He's been through this conference. So our initiation into this area of investigating charged droplets started with our interaction with a group in Bhabha Atomic Research Center, where they wanted to have very well characterized aerosol particles through an electrospray kind of setup. And so they had a typical setup of this kind. There is a needle through which a liquid is pushed out. In the electrospray context, electric field is applied and a spray is formed. And they had a way of neutralizing these particles eventually and measuring the particle size. Okay. Now it's known that when the liquid droplets issue out of an electrospray, typically they are of the order of sizes of the order of tens of microns. And when they measured the size in this region, the size went down to tens of nanometers. And so the size changes from around tens of microns just outside the electrospray needle to size of around tens of nanometers and maybe even further lower. And this is kind of dependent on the conductivity of the solution and so on. It's kind of known in the literature that the conjecture is that multiple Coulombic fission happens of these droplets, and which finally leads to reduction in size. So this was how we got started into trying to investigate the Coulombic fission of charged droplets. And of course, the first time it was Lord Rayleigh who suggested that a charged droplet can lose its instability. I'll use this screen on the left with my pointer. Can't switch between the two. It's easy to understand what the critical charge a droplet will hold. By simple energy calculations, you have a Coulombic energy and the surface energy. If you minimize, you see that there will be a critical charge beyond which the droplet would want to become unstable. And it's given by this expression. For today's talk, I will use a value of 8 pi to be the critical charge, suitably non-dimensional. Okay. Now, what Lord Rayleigh did was a stability analysis of the charged droplet, and in the inertial limit and the viscous limit, you can get the dispersion relation. And what it essentially says is that if you perturb the surface of the drop with Legendre polynomials, then the second Legendre mode gets unstable, the L equal to 2 mode, and that's because it has the least surface energy cost. Okay, so this was kind of known, first discovered by Lord Rayleigh 1882, but systematic experimental investigations, the first systematic experimental evidence came only in 2003. I'll be talking about that. The main reason why there was such a delay for systematic experiments was the very rapid motion of these charged droplets in the electrospray zone. For example, here the velocities of these droplets would be of the order of hundreds of meters per second, and the residence times will be of the order of few milliseconds. Okay. So this prevented systematic investigation of this instability. You would have wanted to observe that the second Legendre mode indeed becomes unstable and so on. So in this context, I would also like to talk about electrospray ionization, which is what Professor Fenn got Nobel for. And the technology here, of course, it's a common instrument in labs, is to basically characterize biomacromolecules. You want to know the charge to mass of these biomacromolecules, and what you do is have an analyte solution, electrospray it, and then it undergoes this multiple Coulombic fission, and then you have biomacromolecules actually in the air, and then you want to take it to a detector and do the charge to mass estimation. And the way you direct these biomacromolecules to the detector is through a quadrupolar trap, which was first suggested by Professor Paul, and it's called as the Paul trap. So the Paul trap essentially has these two electrodes which are at the same polarity, and these two at the other polarity, and then you can apply an AC field. Now, these two concepts are the ones which allowed first systematic investigation of Rayleigh instability, and that was done by the group of Professor Leisner in Karlsruhe Institute of Technology, where my PhD students are now doing postdoc with Professor Leisner. And what they did was trap a charged droplet in a quadrupole trap. So instead of letting the charged droplet go in an electrospray, you have an arrangement where you trap the charged droplet in a quadrupolar trap and observe. And when they observed, what they saw was that the droplet stays here. It gets trapped. I'll talk about the trapping action. It gets trapped. It evaporates, builds a critical charge. So when you introduce the trap, it has a charge less than 8 pi, and then it builds a charge 8 pi and then undergoes this instability. And if you look at the time scale, it is of the order of few tens of microseconds. So it's an extremely fast process. You see the spheroidal mode here, and then a jet is issued out. When the jet is issued out, you lose charge and mass. The charge goes below the Rayleigh charge, then it comes down and through capillary oscillations. Now, we tried to do simulations. I use boundary integral method developed in our lab for simulations, and we use two kinds of models. We use the perfect conductor model. The perfect conductor model, you assume the droplet to be an isopotential, and you find that it forms Taylor cones, and it stops. Because you have an assumption of isopotential. Okay. We, however, use this in a very, I would, in hindsight, I now feel a smart way to actually estimate how much charge it loses, but that's not the focus of the talk today. Clearly, the perfect conductor model cannot predict the formation of the jet, and so we included finite conductivity. And once you include finite conductivity into the system, then you would see that a jet is issued. Now, there are reasons why typically simulations in this area were always done with perfect conductor model, and we are amongst the first ones to include finite conductivity and see issuance of a jet. So this is in the backdrop. Now, so we tried to do these experiments in our lab. I cannot do these experiments here, but I've got the trap for you to see, so that it's easier for me to explain. So the trap, this is the trap in our lab. These are the two end caps which are kept at the same potential, and this is a ring electrode. So this is a ring. These are two end caps, and then you would have some syringe through which you introduce a charged droplet here, and the droplet comes here and it gets levitated. So that's how it happens. What you do is between these two end caps you put an AC field. So these two end caps are at the same potential. The ring is at this. This is grounded. This is live, and between them you apply a potential. So that is what this was our embodiment of the trap. It was not as sleek, I would say, as the trap by Professor in the Leisner's group. But then in hindsight, we feel that this is what led to a new. This is in fact what led to the talk which I presented today. And so what we saw in Mohit, the experiments were done by my students Mohit, and what he saw was these oscillations of the droplet in the trap, and then the droplet built a critical charge at some point due to evaporation, and then it evaporates. So let me give you roughly the idea. It's an ethylene glycol drop around 100 microns in size. It takes around 5 to 10 minutes when it is levitated in the trap to build a Rayleigh charge, and then the instability happens in around 100 microseconds. Unlike the experiments by Professor Leisner's group, where they had time-lapse imaging or a CCD using a CCD camera, we used a CMOS camera, 200,000 frames per second, a 2-second video captured this event, and the whole instability would be hardly around 20 to 30 frames. So that's it. Now the question for today's talk is why do we see an asymmetric breakup in our experiments? There is an up-down asymmetry as you see in our experiments. And when the experiments were done, we did experiments on around 40 to 50 droplets. Almost in 90% of the cases, the droplet broke upwards. and in 10% of the cases it broke down. Okay. And so we really wanted to understand why the droplet predominantly broke upwards. And that's the focus of my talk today. So so as I said, this was the setup. Now I can directly come to the potential part. So normally we know that if you have two parallel plates, you apply potential between them, the electric field is constant. In the trap like this, you realize what is called as which is basically a quadrupolar potential field. That's the reason why it's called a quadrupolar trap. So what you have here is an electric potential which is given by the second Legendre mode, the growing harmonic. P2 is the second Legendre mode. And if you represent in cylindrical coordinates, this is the expression. Lambda is the intensity of the trap. It's related to the voltage applied to the end caps with a suitable length scale. And what you see is that the potential as well as the electric field at the center of the trap is 0. And as you go away from the trap, it increases. And this is critical, as you would see, for levitation. Okay. So so we did experiments on this. This again not focus of my talk, but we could levitate several charged droplets into the trap, and we could get nice Coulombic crystals. We could get degeneracy in the system. For example, if you put 4 droplets, you get a quadrilateral system or a triangular system with a drop in center, depending on the Q by M ratio. So this is all we could do. So let me try to explain, attempt to explain to you what's the origin of the restoring force. Why does, if any charged droplet, if you put in a trap, why does it come to the center? So I'll explain it through this picture. So these are our end caps. This is the ring. Let's focus on the end caps. And we can consider a positively charged droplet or a negatively charged droplet, doesn't matter. But I'll try to explain it with the positively charged droplet. So imagine that the end caps are at the positive cycle. The positive droplet is here. It encounters a repulsive force which tries to take it to the center of the trap. Okay. Now when the cycle changes, the droplet is attracted towards this end cap. So if you look at the lower end cap, in this cycle it is pushed towards the center. In this it is pushed towards the end cap. But this force is stronger than this force because the field here is stronger than here. Okay. So on an average, you see that a correlation of the AC field applied to the end cap and the oscillatory motion of the droplet leads to a net attractive force on the charged droplet towards the center of the trap. So this really is the restoring force, origin of the restoring force, which is at the center of why charged droplets can get trapped at the center. Okay. So I'll try to quickly run through a small derivation here. What you see here is, so there is an electric potential, you would want to write an equation of motion. Now in Professor-Leisner's group, and that is where the difference we got between their results and our results, additionally on top of the AC field that they apply across the end cap and the ring, they had a DC bias to balance the weight of the droplet. This is very similar to the Millikan's experiments to determine the charge on an electron. You put a DC field, you levitate the oil droplet with an electron, you balance the weight with the electric field, and then you determine it. So they had the weight being balanced by a DC bias. And so if you write the equation of motion for the center of mass, so this is the droplet, this is Z, tells you the center of mass position of this droplet. You have an acceleration and a friction term and a QE force acting on this droplet, which is position dependent now because the potential itself is quadruple in this region. Now remember here that the weight is getting balanced by the DC bias in Professor-Leisner's group. Okay, so this is the classic case. If you solve this is a Matthew equation again, and if you solve this numerically, you see that there is a fast oscillation of this center of mass and then a slow progression towards the center. Okay, so the droplet does oscillations and then comes to the center of the trap. Okay, so you could write the Z position as a sum of the oscillatory position S and the average position, time average position Z bar. And if you do that and ask that the oscillatory position averages to 0, you can write an equation of motion for the fast oscillatory part where Z bar is constant, and you get a time periodic solution for the oscillatory part of the motion. And then knowing this, when you write the equation for the average position of the droplet in the trap, you find that there is a restoring force which is actually a correlation of the fast oscillation of the droplet and the AC field applied to the end cap. And this is in line with the physical argument that I gave, that the fast oscillations together with the end cap cycles gives rise to a restoring force. So if you look at the equation of motion for the center of mass, the average center of mass, it looks like this, and a nice spring constant comes up, which actually is related to the time correlation of this, right? So what you have is this clearly tells you that in such a case the droplet would come and settle at the center of the trap. Now in our case we didn't have a DC bias, and because we didn't have a DC bias, we couldn't balance the weight of the droplet. So the weight of the droplet now comes into the equation of motion for our case. And if you repeat the same exercise, what you find now is that in the case of a DC bias in Professor Leisner's group, you see that the droplet comes and settles at the center of the trap. In our case, because there is no DC bias, the weight is actually balanced by the trap force. And when the weight gets balanced by the trap force, the droplet is not levitated exactly at the center of the trap, but it's levitated off center. Now the field at the center is zero. So in Professor Leisner's group, when the drop comes to the center of the trap, it doesn't oscillate, it remains there. But in our case, because the drop gets levitated off center and the field there is not zero, it starts doing oscillation around the average position. So this really is the center of mass oscillations that you see around the average position. Okay. And this again, let me play the video. Now an important point to note here, which is relevant to the story, is that the applied potential, which is this red curve. So if you see the applied potential, when the end cap is positive here, the end cap is negative here, you see the center of mass, it is out of phase by pi, which means that when the end cap is positive, the droplet is here. When the end cap is negative, the droplet is far out. And this again is going to be central to what we've observed. Okay, so thing to remember is that the droplet it is out of phase with the applied voltage. Now the droplet not just does center of mass motion, it also does surface oscillations and surface deformation. So the two are coupled. So the whole idea here is that there is a deformation translation coupling which actually is responsible for what we see in the experiments. So let me put it out here. This is the potential of the end cap. The end caps are negative here, the end caps are positive. Okay. Now if you have a neutral droplet, it will always get prolately stretched irrespective of whether the end caps are negative or positive because of the change in polarization. But if you have a charged droplet, like in the present case, we see that when the end cap is negative, the droplet is prolately stretched. When the end cap is positive, the droplet is oblately stretched. So we could do a viscopotential theory, write the shape modes for the different Legendre modes. This will give you the center of mass, and these will give you the shape oscillations. And there is some agreement between the experiments and this. Now, so the point to be taken from this analysis is that when the end cap is negative, we saw that when the end cap was negative, the droplet is farthest from the end cap and it is prolately stretched. And when the end cap is positive, it is nearest to the end cap and oblately stretched. Okay. Now, this you see in the experiments as well. So I plot. So these are the experimental positions and deformations. So you see that the droplet does its prolate, it comes down, becomes oblate, prolate, oblate, prolate, oblate, prolate, and then it breaks. And it breaks, releases the charge, mass, and then oscillates, comes back. Okay. Now if you plot this, this is the aspect ratio. Aspect ratio greater than 1 is prolate, aspect ratio less than 1 is oblate. Here I plot the polarity of the end cap, and here I plot the center of mass position. So let's look at point B. B is this shape. It is oblately shaped. It's not as easy to decipher from the images if you go to image A, but you see that at this point B, the end cap is negatively charged. Where am I? So here. So this is point B. The end cap is positively charged. The center of mass is negative, which means it is closer to the end cap, and the aspect ratio is it's an oblate shape. So you see an oblate shape, and in the next cycle, the end cap is negatively charged. The center of mass is positive, it is farther away from the end cap, and the deformation is prolate. So you see this prolate deformation. Okay. Now, this was all theory, analytical theory. We wanted to do boundary integral method calculations. we had difficulties including the viscous terms in our boundary integral calculation. So we had a purely potential boundary integral code. And what you see here, so therefore these oscillations are really because we do not have any damping in our EM code. But what you see here is that when the end cap is positive, this is the end cap potential. When the end cap is positive, the center of mass is negative. And when the end cap is positive, the deformation is oblate, and vice versa. When the end cap is negative, the deformation. So this is in line with what I've already been telling you. But then we could actually simulate the system. And I show here experiments and the boundary integral calculation side by side, and you would see that it breaks in the upward direction. Yeah. Now, so in the boundary element calculations, we actually put charge by hand and see the oscillations. We do not simulate evaporation here. So you have to put some charge on the droplet, and then it of course oscillates and deforms by itself in the VM formalism. So we put a charge about, yeah. So remember the critical charge is 8 pi. So we start with a charge less than 7.7 pi. Okay, and so it's expected to be stable, and so it does center of mass oscillations, and it is stable as you see. But as soon as you put a charge of 7.7 pi less than 8 pi, so remember 8 pi is the critical charge, you put a charge of 7.7 pi, and you see that the droplet gets prolately stretched in the negative cycle farther from the end cap, and then as the cycle changes to positive, so the droplet here is now trying to undergo a Rayleigh instability, and as it undergoes the Rayleigh instability, the polarity of the end cap has changed and it undergoes a upward breakup. Okay, so now so we see an upward breakup at a charge less than 8 pi at a value of 7.7 pi. In the code, we can put a charge of greater than 7.7 pi. We put a charge of 8 pi. You see that it has got prolately stretched when the end cap is negative. But now, because the charge is more, the rate of instability is faster. Before the end cap can change sign, the Rayleigh instability is set in, and now the droplet breaks in the downward direction. Now clearly the 7.7 pi charge is reached earlier than 8 pi, and so that's the reason in experiments you predominantly see upward breakup. That's what we feel at least. Now there's a little more to this, that it is known that the bifurcation of a charge, the Rayleigh fission, is actually a transcritical bifurcation. So it was first given by Samopoulos and Brown, by Busser and Scriven later, and we realized this in the viscous limit. The other calculations were always in finite Reynolds number or in potential limit. And what it essentially tells you is that there is a bifurcation point 8 pi, at which of course the spherical shape becomes unstable. But there are also two branches to the solution, a prolate branch and an oblate branch, and the oblate branch is supercritically stable, the prolate is subcritically unstable. And then the two meet at a point, and that's the reason it's called transcritical bifurcation. And so what it means is that the oblate shapes of course are always stable, and that's the reason when we get oblate shapes in our oscillations, they never break. So you see here the oblate shapes are always, the oblate shapes will never break. These shapes will never break, for example. I think I had a better picture, but I don't get it now. But the prolate shapes can break, and the prolate shapes can undergo subcritical instability if the initial amplitude is larger than a finite one. And so this is what we think is really happening in our experiments. The up-down oscillation of the charged droplet in the trap leads to prolate deformation, and when there is a prolate deformation, it leads to finite amplitude initial perturbation that leads to the Rayleigh instability, and then the instability is subcritical. So you get an instability at a charge less than the Rayleigh critical charge. So this essentially is the essence of my talk. If the charge is greater, of course, the growth rates are higher. So we feel that this is at least the first realization of subcritical instability in experiments. I know you would be doubting about the base state itself because it's oscillating, and so it's not really spherical and all. So we okay. So let me just track back a bit. Is this esoteric? Is this thing esoteric? I feel that asymmetric breakup is more of a rule than an exception. This is what is seen in electrospray experiments, first reported by Tang and Gomez. They provocatively titled the paper as Caught in an Act, where a charged droplet was pictured and actually seen to undergo asymmetric instability. We also saw this in our experiments. We've done this in other context earlier. The experiments came much later, and we are kind of trying to see what problems we could solve and solve these problems, construct bifurcation diagrams. But we now feel that we've actually seen it in our experiment. Now, this is the 7.75 picture point that I presented in today's talk, and you indeed see that it undergoes. So I showed the schematics earlier, but this is the actual transcritical bifurcation diagram, and you see this point lying here, really admitting the subcritical instability. So with this, I think I'll stop. This is my appendix slide, or the supplementary slide. These are my viscous viscous boundary element formalism. This is my potential flow boundary element. So I'll stop with this, I think.
Long live India and France friendship.